Hi, good day. So one of the things that we encountered in classifying salts is the word dissociation constant. Now, dissociation constant is symbolized with capital letter K, and it is a number that describes the molar concentration of conjugates that will dissociate or that will be produced from one molar acid or base once that acid or base is dissolved in water. Take note that dissociation constant is constant for each molecule or for each compound. Each molecule or each compound has their own dissociation constant, and dissociation constant is considered unitless. Why? Because here, essentially, dissociation constant is the ratio between molar concentration of conjugates and molar concentration of its acid or base. And so, the molar concentration here, this one and this one, will be cancelled out, causing the dissociation constant to have no unit at all. To understand this concept further, let us have here an example of dissociation constant. And by the way, there are actually two types of dissociation constant. The dissociation constant for acid, that is Ka, and the dissociation constant for base, that is Kb. Okay? Now let's have here the dissociation constant for chlorous acid, HClO2, chlorous acid. Now, the dissociation constant for chlorous acid is determined to be 1.1 times 10 raised to negative 2. What does this number mean? This number only means that for every 1 molar of HClO2 or for every 1 molar of chlorous acid, there will be 1.1 times 10 raised to negative 2 molar of hydrogen ion, which is actually our conjugate acid, and chloride ion, which is actually our conjugate base, that will dissociate from our parent acid, which is our HClO2. Okay, in Tagalog, itong HClO2 natin, maghihiwalay siya into H and ClO2. Okay, and according to our dissociation constant here, sa paghihiwalay niya, kapag tinunaw natin ang 1 molar ng HClO2 sa tubig, it will always produce 1.1 times 10 raised to negative 2 molar of H positive and ClO2 negative combined. Now, how are we going to express the dissociation constant formula? For us to be able to understand how we express the dissociation constant formula, it is necessary for us to go back with the topic Bronsted-Lowry acid and base definition. Now again, according to Bronsted and Lowry, water can act both as an acid and as a base. If it is combined with an acid, then it can act as a base. And if it is combined with a base, then it can act as an acid. Now let's have here an example. Let's say for example, a hypothetical acid HA is dissolved in water. Okay, so we have here H2O. Now because HA is actually our acid here, water will now act as a base here. And as an acid, this HA will now donate hydrogen to the water. Okay, so from this one, it will donate hydrogen to the water, and it will turn the water into H3O positive, which is actually read as hydronium ion. Okay, now this hydronium ion is our conjugate acid here because it actually came from a base. So again, ang magka-partner lagi ay base and conjugate acid and conjugate base. Okay, so this is our base, and it turned now into H3O positive, and this is now our conjugate acid. On the other hand, our HA here, after it donated hydrogen, it turned into a negative. From an acid, it turned into a conjugate base. Okay? Now, generally, water molecule does not really change that much when an acid or base is added to it. That's why sometimes water is actually negligible in this equation. Okay, and instead of writing HA plus H2O will yield to H3O positive plus A negative, instead of writing that, okay, we sometimes omit this H2O because of its negligible effect to the solution, and therefore turning into HA. Okay, and after we dissolve this HA into water, it will produce H positive, okay, and A negative. But both of these equations, or both of these chemical equations are actually correct. Now take note that these reactions are in equilibrium or happens reversibly, which means that because it happens reversibly, it can actually achieve an equilibrium point, a point wherein the rate of production of your conjugate acid and conjugate base is the same as the rate of production of HA and water. Okay, so that's why dissociation constant is also known as equilibrium constant. Now, for us to be able to write the dissociation constant, essentially the general formula for us to be able to write the dissociation constant for an acid or base is molar concentration. These brackets represent molar concentration. So molar concentration of product, in this case the product is always located at the right side of the equation, over the molar concentration of reactant. In this case, the reactant is always written at the left side of the equation. So these are the reactants and these are the products. Okay, and both of them are actually raised to n and m. Now n and m here represents the stoichiometric coefficient, the number that can be found in front of each reactant or each product. So let's say for example we have two here, okay, and now that two is actually our stoichiometric coefficient, and therefore we can actually write it here. Okay, so that's actually the general formula for dissociation constant expression. Now for this one, let's write the dissociation constant expression or formula for this equation. So again, as we said earlier, water will have a negligible effect to the solution. So its change is very minimal. Its change is very minimal because in a solution with acid, water will always have the greatest amount. And so it will have negligible effect to the solution. So we can actually what do you call this? We can actually cancel this water out, and we can have here Ka is equal to molar concentration of H, or we can also write H3O positive. That's just fine. Okay lang 'yun basta nandyan yung ating conjugate acid. So molar concentration of H positive or H3O positive, parehas lang 'yon. Raised to 1 because we have here 1 invisible 1, or we can also omit this 1 here. Okay, multiplied to the molar concentration of A negative, which is actually our conjugate base. Now, take note that both H and A here are our products. So they are both found at the numerator side, and they are actually multiplied, not added to each other. Okay, so they are multiplied to each other over the molar concentration of reactant. In this case, the reactants originally are the acid, the parent acid, and water. But again, water has negligible effect to the solution, and therefore we can cancel this one out, and we can have here only the HA, or the parent acid, raised to 1, which is the stoichiometric coefficient of HA, or we can omit this 1. Okay? And therefore this is now the dissociation constant expression or formula for this example. Now let's have here another example, or other examples, on how we can write the dissociation constant expression. Okay, so let's have here letter A, carbonic acid, and once it is dissociated in water, it will produce positively charged hydrogen, one positively charged hydrogen, and bicarbonate ion. So our conjugate acid here is H positive, and our conjugate base here is our HCO3, or the bicarbonate ion. Now again, the dissociation constant expression is product over reactant. And if we have multiple products or multiple reactants, we are just going to multiply those multiple products to their fellow product, or to multiple reactant, or to their fellow reactant. Okay, so we have here Ka, why Ka? Because carbonic acid is an acid, so we have here Ka, not Kb. So Ka is equal to molar concentration of H positive, that is actually in our product side, multiplied to the molar concentration of HCO3 negative, and we have here invisible 1, okay, over the molar concentration of the parent, which is H2CO3. Now again, we omitted H2O because it has negligible effect to the solution. Okay. Now for letter B, we have here ammonia plus water will yield to ammonium ion plus hydroxide ion. Now in this case, ammonia is considered base, and since ammonia is a base, then water will act now as an acid. Now as an acid, water will now donate hydrogen from the to the NH3. So from water, okay, it will donate hydrogen to our NH3 molecule, and it will become, NH3 will now become NH4. Now NH3 is a base, therefore NH4 positive is a conjugate acid. And as you have noticed here, all positively charged ions are always conjugate acids here, and all negatively charged ions in the right side of the equation are always conjugate bases. So after it donated hydrogen to NH3 molecule, it now NH3 molecule now turned into NH4 positive, which is now our conjugate acid, and H2O, after it donated hydrogen to the NH3, it now turned into OH negative. Okay, why negative? Because again, hydrogen is positively charged. Okay, and once you lost a positively charged hydrogen, of course you will now become negatively charged. NH4 is positively charged because, as you have noticed here, it actually received positively charged hydrogen, and as you receive positively charged hydrogen, of course you will now also become positively charged, and therefore NH4 is positively charged. Now our products here are NH4 and OH, so or those are the products that can be found on the numerator side, and our product here, our reactants here are NH3 and H2O. However, again, H2O has negligible effect to the solution, and therefore we can cancel this one out, and instead of writing NH3 multiplied to H2O, we can just write NH3. So we have here Kb, dissociation constant for base, because NH3 is a base, not an acid. So Kb is equal to molar concentration of NH4 positive, okay, multiplied to the molar concentration of OH negative, and again meron silang exponent na invisible 1, okay, over the molar concentration of NH3, and si water kinancel na natin. Okay, so that is how you can actually write the dissociation constant expression. So that's all. Thank you for listening, and goodbye.